Let's continue our related rates lesson with a second example. And again, we're going to work lots of examples. This turns out to be a classic related rates problem for elementary calculus, and it's our first one that actually puts us in a right triangle, and we see a lot of problems that have us in a right triangle. So let's read the problem. A ladder 10 foot long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Well, let's start to talk about process for solving related rates problems. One of the first things that I do in solving a related rates problem is to draw myself a picture. I am extremely visual, and it helps me to understand the relationships that are going on. So there's my vertical wall, there's my floor, and here is my ladder. Now, when I have vertical and horizontal things going on, I kind of sort of imagine myself in the plane. And so here is this ladder, and the ladder is 10 foot long, and as it's sliding down the wall, that never changes. The ladder is always 10 foot long. I'm going to call any horizontal distance, I'm going to call that x. And any vertical distance, I'm going to call that y, for two reasons. Number one, I'm comfortable with x and y. And number two, I'm comfortable with being in the plane. So if I can bring variables in that make sense to me, then I'm going to use those variables. Now, could I say that this was F for floor and this was W for wall? I absolutely could, but I'm comfortable with x and y. So I'm not going to say that the choice of any other variables is incorrect. It's not. You get to choose your own variables. But we're going to practice choosing variables that are easy for us to use, intuitive for us to use, and therefore we can find the relationships that are involved. So I have a ladder 10 foot long that rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate, well, I've already called the vertical distance x. So the rate at which that vertical distance is changing, I'm going to call dx dt, because it's sliding over time. Time is in charge of the rate at which it's sliding. And this is the positive direction in the plane for the x-axis. So this is going to be a positive rate. And they tell me in the problem that it is a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall? Well, I've already called that vertical distance y, so I'm going to call this rate of change of that vertical distance dy dt. And it's sliding down. The y distance here vertically from where the ladder touches the wall to where it slides down, that vertical distance is decreasing. And we remember that when a variable is decreasing, when a function is decreasing, its derivative is going to be negative. So that tells me that as my ladder is sliding down the wall, dy dt will have to be a negative value. And that's what it's after. How fast is that sliding down the wall? So there's my question mark. And it wants to know it at one specific time, when the bottom of the ladder is 6 feet from the wall. So it wants to know it specifically when x is 6 feet. So there's all the information using really good notation that I get from the words in this related rates problem. Now, the very next thing that I do after I draw myself a picture and label everything appropriately and come up with good notation is I've got to come up with a relationship between all the variables involved. I need a relationship between x and y. Well, very clearly, I'm in a right triangle. I go back to geometry and I say, hey, I know that there is a relationship between the legs of a right triangle and the hypotenuse of that right triangle. It is x squared plus y squared equals 10 squared. So there is my relationship between the two variables that are involved. So now my next step is to find a relationship between the rates. Now I need the related rates, because the information that they gave me involves dx dt, the rate at which x is changing, and dy dt, the rate at which y is changing. So again, what do we use to find rates in a related rates problem? Where does the derivative come in? It comes in through implicit differentiation. So I'm going to take the relationship between x and y and find the relationship between dx dt and dy dt. I'm going to implicitly differentiate with respect to time. So again, these two terms are going to involve the chain rule. They involve the chain rule because I'm not differentiating with respect to x or differentiating with respect to y. I'm differentiating with respect to time. So both of them involve the chain rule. So it is the derivative of the outside, not changing the inside, times the derivative of what's inside with respect to time. So there's what the derivative of the first term is with respect to time. In implicit differentiation, we just copy down our pluses, our minuses, and our equals. So I'm copying down my plus sign. Now I want to implicitly differentiate this term. It's the derivative of the outside, not changing the inside, times the derivative of what's inside. So there's the rate at which that term is changing over time. And copy down my equal sign. This is a constant. The length of the ladder never changes in this problem. It didn't call it an extension ladder. If it did change, if it was an extension ladder, I wouldn't use the number 10. I would use a different letter like H or something for hypotenuse, and then we would see how it was changing with respect to time. But it's not changing. Over time, the length of that ladder doesn't change, and the derivative of a constant is 0. Now I've got to find all the players. I have 4 variables. I have x, I have dx dt, I have y, and I have dy dt. Now, the one that they're asking me for is dy dt. This one is the one that I want to solve for. So I better have a value for all the rest of these variables. That's the only way I can solve for dy dt and actually answer this question. Well, I know what x is. They told me. They want to specifically know when x is 6 feet. Now, I can do some algebra right now, and I can divide every term by 2. 2 divided by 2 is 1. 2 divided by 2 is 1. 0 divided by 2 is 0. So I'm going to have x, which they told me was 6, and dx dt, which they told me was 1. They gave me that one as well. Now I'm going to have y. Well, they didn't give me y. And I'm going to solve for dy dt. That needs to be my one and only variable that's left. But I got to figure out what's going on here. How can I find out what y is when x is 6 and my ladder is 10 foot? Well, that's the Pythagorean theorem. If I'm in a right triangle and I know 2 side lengths to that triangle, I can find the third side length. So that's what I'm going to do. I am going to use 6 squared, that's x, plus y squared, plus y squared has to equal 10 squared. And that's how I'm going to find the value of y when x equals 6. So 36 plus y squared equals 100. Subtract 36 from both sides, y squared equals 64. And y, yes, mathematically equals plus or minus 8. But let's talk about context. Never forget the context that you're in when it comes to doing your mathematics. And when we're talking about a distance that's being measured against a wall, do we ever have negative measure? Am I going to say that that distance is negative 8 feet? Never. So even though algebraically it would make sense to put plus or minus 8, In the context of this problem, the only value that makes sense is 8. So we're going to come back over here, and we're going to plug in 8. So we have 6 plus 8 dy dt equals 0. So 8 dy dt equals negative 6, and dy dt equals negative 6 eighths, which reduces to negative 3 fourths. So there is the work that we need to answer our question. And are we glad that it's a negative value? We absolutely are. We said up front that if that distance was decreasing, its derivative would have to be negative. So again, I'm going to give myself some space. You can write this beneath where we are, but they ask us in words, so we answer in words. How fast is the top of the ladder sliding down the wall? The top of the ladder is sliding down the wall at a rate of 3/4. What are the units? Here are the units for the horizontal change. They're going to be the same for the vertical change. And you said, but wait a minute, it's negative 3/4. Well, in words, I took care of the negative with the words sliding down. The top of the ladder is sliding down, meaning negative, the wall at the rate of 3/4 feet per second. There's our second example, our second related rates problem. One thing that I would like to say is that the ladder is a classic related rates problem because, number one, you see it all the time. I can almost promise you that there's going to be a multiple choice question on your exam in May that is a sliding ladder related rates problem. They're fairly straightforward, they're not difficult, they're not time consuming. If you get a difficult or complicated related rates problem, it's going to be a free response problem. So you're going to see related rates problems that put you in a right triangle a lot. So even though this has to do with a ladder sliding down the wall, there are lots of other contexts, lots of other situations that they could put you in and ask you about the rate at which one side of a right triangle is changing when this or that is happening. So look for it. It's something that happens a lot, and it's something we need to be really comfortable doing. I think we're close enough to the end of this video. I think I'll go ahead and stop here, and we'll take up the other examples in a third video. So watch for that.